So, got some smart boy stuff today, and you know that because I've got my glasses on, so we're really ready for a spicy treat. Today we're going to be using the definition of E as being the limit as n approaches infinity of 1 plus 1 over n to the n to show that the function e to the x differentiates to itself. So, how are we going to do this? Well, first of all, we need a slightly more strong result than this. Because it turns out if n approaches negative infinity, this expression will still approach e, and I'll show that now. So what we'll have to do first is change this 1 plus 1 over n to an n plus 1 over n, the n. And now, if I raise this side to the power of minus 1 twice, that's just the same as raising it to the power 1, which is exactly the same. Just as long as it's not 0, which is fairly clear. So, raising to the power of minus 1 the first time. Oh, what am I doing? That's not a fraction. Right, raising to the power of minus 1 the first time, we'll change this n plus 1 over n to an n over n plus 1. And raising to the power of minus 1 the second time, we'll turn this to the power n into the power minus n. So this is exactly the same as that. And now, I'm going to write this n over n minus 1 as 1 minus 1 over n plus 1. I hope you see that that's absolutely fine. And now I'm going to multiply each side by an expression, which is limit as n approaches infinity of 1 minus 1 over n plus 1 to the minus 1. And if I multiply this side as well by that, then the minus 1 and the minus n would add to minus n plus 1. But of course, I can just evaluate this limit on this side, and as n approaches infinity, this will approach 0, so this whole thing will approach 1. 1 to the power minus 1 is, of course, 1, so we get e equals limit as n approaches infinity of 1 minus 1 over n plus 1 to the negative n plus 1. And now if I let some number m be equal to negative n plus 1, then when n approaches infinity, m will of course approach negative infinity. And so e is the limit as m approaches negative infinity of 1 plus 1 over m to the power m. So, now that we have our stronger result, we can find an expression for e to the x as a limit of this kind of form. So first we'll just concentrate on our earlier result for e, and then we'll focus on the result as n approaches negative infinity as well. So if I raise each side to the power x, of course raising this to the power of x just means we can bring down the exponent of x to multiply by this n, and we get limit as n approaches infinity of 1 plus 1 over n to the power nx. And now we can let m equal nx. And if we divide both sides of this equation by mn, then we would get that 1 over n equals x divided by m. We also know that if x is less than 0, then as n approaches infinity, m will approach negative infinity. And if x is greater than 0, then as n approaches infinity, m of course will approach positive infinity. And so, considering these cases of x less than 0 and x greater than 0, we have for x less than 0, this e to the x will be the limit as m approaches negative infinity of 1 plus 1 over n. Well, 1 over n is just x over m. So 1 plus x over m to the power nx, but nx is just m. And for x greater than 0, we get e to the x is going to be the limit this time as m approaches positive infinity of the same expression. However, that's just using this definition of e here, the limit as n approaches infinity. If we use the limit as n approaches negative infinity, I'll draw this in another box, then this gets us x less than 0, again letting m equal nx. This time if x is less than 0 and n approaches negative infinity, then n will approach positive infinity. So we'd get e to the x equals limit as m approaches positive infinity of 1 plus x over m to the m. And for x greater than 0, e to the x equals limit as m approaches negative infinity of 1 plus x over m to the m. And now we can combine these two. So for x less than 0, we have e to the x equals limit as m approaches negative infinity and positive infinity of the same expression. And for x greater than 0, we have e to the x equals limit as m approaches infinity and negative infinity for this expression again. So now we can say just for any x not equal to 0, for any real x, so for x in reals, such that x is not equal to 0, we have e to the x equals the limit as m approaches infinity of 1 plus x over m to the m, which is equal again to the limit as m approaches negative infinity of 1 plus x over m to the power m. And actually we can even get more specific than this, because we don't have to specify this x is not equal to 0, because if we consider x equals 0 in this expression, well, the left hand side, e to the 0, is of course just 1. The right hand side, well, 1 plus 0 over m is just 1, and 1 to the power of m, no matter what that m is, will always be 1. So for any real x, actually, we don't need to specify this x not equal to 0. And now we get on to the final part of proving that e to the x differentiates to itself. So we want to consider the function f of x equals e to the x, and we want to show that f dash of x equals f of x. Well, how can we possibly do that? What we'll do is we'll use the definition of the derivative. And the definition of the derivative is that for a function f of x, the derivative f dash of x is equal to limit as h approaches 0 of f of x plus h minus f of x divided by h. And so if we substitute f of x equals e to the x in here, then we get f dash of x is equal to the limit as h approaches 0 of f of x plus h, well that's e to the x plus h, minus e to the x here divided by h, which is equal to, what we can do is we can take out a factor of e to the x, so e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now straight away you can see something really cool about exponential functions. This works generally for any exponential function if you had, say, just a general b to the x rather than special e to the x, which is that this part outside here is just f of x all over again. That's a terrible x. There we go. And this part here, this limit as h approaches 0, does not change with the value of x. So this is some constant, which means that for any exponential function, not just e to the x, we have the derivative is proportional to the value of the function at that point. And e to the x is the special function which has the property that it is not just proportional, but equivalent. And so if we let k equal this limit as h approaches 0 of e to the h minus 1 over h, then f dash x equals k f of x. And what we want to prove for e to the x is that this k is equal to 1. So how on earth would I show that k is equal to 1? Well, what it will be helpful to do is to consider what this limit as h approaches 0 really means. And what it means is that if I choose any epsilon greater than 0, then I can always choose a small enough h, closer and closer to 0, such that e to the h minus 1 over h is within epsilon of k. And so this within epsilon of k I can write as e to the h minus 1 over h minus k. The absolute value of that would be less than epsilon. This is just the distance on a number line. And so this is the same as saying that negative epsilon is less than e to the h minus 1 over h minus k is less than positive epsilon. And I can do some rearranging now. I'm going to add k to each side. So then I get this. And I'm going to multiply each side by h. So we'll do the middle first. That becomes an e to the h minus 1. This becomes hk plus epsilon. And multiplying this by h here. Now I can add 1 to all three expressions. And so 1 plus k minus epsilon h is less than e to the h is less than 1 plus h k plus epsilon. And now I'm going to raise each side of the equation to the power 1 over h. And so, of course, the middle will just change from e to the h to e. The left-hand side will be raised to the power 1 over h. The right-hand side will be raised to the power 1 over h. And so, for any epsilon greater than 0, I can always choose a smaller and smaller h such that this inequality will be true. Now, if I let m equal 1 over h, this is the same as saying that h equals 1 over m, of course. And h approaches 0. Well, what happens as h approaches 0? M will approach either positive or negative infinity. And now this statement about taking h smaller and smaller and smaller can be changed. So now that I'm saying that for any epsilon greater than 0, instead of choosing a small enough h, I'm choosing a large enough m such that the following expression will be true. 1 plus k minus epsilon times h is the same as dividing by m to the power of m is less than e is less than 1 plus hk plus epsilon. Well, the h is just 1 over m, so that's 1 plus k plus epsilon over m. To the power of 1 over h is to the power of m again. And so for any epsilon greater than 0, I can always choose a large enough m such that this inequality is true. And that's as m approaches positive or negative infinity. And in that case, I can let m approach infinity. And then for any epsilon greater than 0, it will always be true. So letting m approach positive or negative infinity on this side gives us, well, by this work we did earlier, that would be e to the k minus epsilon is less than e is less than, this side would become e to the k plus epsilon. And so this is for any epsilon greater than 0. And so if I consider what happens as epsilon itself approaches 0, then I get that e to the k must be equal to e, because both these sides are converging to the same point, and e is in between both these barriers coming in. And so taking the natural logarithm of each side, natural log of e to the k is equal to natural log of e. Therefore, k equals 1, and therefore, if our function f of x equals e to the x, then f dash of x, k is just 1, so that can disappear. E to the x differentiates to itself. Hope you enjoyed this video, nice spicy one. More videos will come out in future. I am going on holiday soon, so there will be about a 2-week break, but I plan to get back to it very soon. So yeah, hope you guys enjoyed. See ya.